The universe contains objects that outshine entire galaxies. These cosmic beasts generate more energy than hundreds of billions of stars combined. You'd expect the biggest things to shine brightest. That assumption crumbles when you meet quasars. Tonight we're discovering what powers these impossible energy sources. We'll trace how astronomers solved one of space's greatest mysteries. Before we dive into these cosmic lighthouses, drop a comment about what you think creates the most energy in space. If you enjoy these deep space mysteries, consider subscribing. These explorations reveal the universe's most extreme secrets. Radio telescopes in the 1950s detected something that shouldn't exist. Scientists were scanning space with these giant dish antennas that detect radio waves from cosmic objects. What they found broke all the rules. Incredibly powerful radio signals were streaming from tiny points in the sky. These signals were thousands of times stronger than anything ordinary stars produce. Through regular telescopes, these objects looked completely normal. Just faint dots of light scattered across space. Nothing special at all. But their radio emissions told a completely different story. They were broadcasting energy like entire galactic radio networks, yet they appeared no bigger than individual stars. Scientists called them quasi-stellar radio sources, objects that looked like stars but acted like cosmic monsters. The mystery of their true identity had just begun. Astronomers pointed instruments called spectrographs at these mysterious sources. A spectrograph splits light into its rainbow of colors, revealing what objects are made of. Scientists expected to see familiar star signatures. Instead, they found something that shattered every assumption. The rainbow patterns were shifted dramatically toward the red end of the spectrum. This redshift meant these objects were racing away from us at incredible speeds. The measurements indicated distances of billions of light years, objects that far away should be completely invisible to Earth's telescopes. Yet there they were, blazing bright enough to detect across the entire observable universe. This created an energy crisis that broke astronomical rules. To shine this bright from such enormous distances, these objects had to generate more energy than entire galaxies. They were producing the combined light of hundreds of billions of stars from regions no bigger than our solar system. These mysterious objects were violating the fundamental rules of cosmic energy. The math simply didn't work. Nothing could generate this much power from such a tiny space. Scientists calculated the energy output. A single one of these sources was producing power equivalent to trillions of hydrogen bombs exploding every second. And it had been doing this for millions of years without stopping. The energy density was beyond anything known in the universe. It was like cramming the energy output of an entire galaxy into a region the size of our solar system. Normal stellar processes couldn't explain this. Nuclear fusion in stars was millions of times too weak. Even if you packed 1 trillion stars into a tiny space, they still couldn't generate this much energy. The universe had revealed objects that operated on energy scales nobody thought possible. The hunt for their power source became astronomy's greatest challenge. These cosmic powerhouses had another shocking secret. Their brightness wasn't constant. They flickered like cosmic lighthouses, changing dramatically over just hours or days. This flickering revealed something mind-bending about their size. When an object changes brightness, the change can't travel faster than the speed of light. If something dims in one day, it can't be bigger than the distance light travels in one day. Light travels incredibly fast, but even in a full day it only covers about 25 billion kilometers. that's tiny compared to the size of galaxies, which span trillions of kilometers. These objects were generating galaxy-level energy from regions smaller than our solar system. The energy density was so extreme it broke every conventional model of how cosmic objects work. The flickering confirmed that whatever was powering these monsters was compressed into impossibly small spaces. The universe's most powerful energy sources were also among its most compact. Scientists needed a name for these impossible objects. They had discovered sources that looked quasi-stellar, almost like stars, but clearly weren't stars at all. The term quasi-stellar radio source was too cumbersome for everyday use. Astronomers shortened it to quasar, creating one of space science's most famous terms. The name stuck because it captured the fundamental contradiction. These objects masqueraded as stars while harboring energy mechanisms that dwarfed entire galaxies. Quasars became the poster children for cosmic extremes. They represented objects so powerful and distant that they challenged our understanding of what was possible in the universe. But the name was just the beginning. The real mystery was what could possibly generate this much energy from such a compact source. The answer came from the most extreme objects known to science: supermassive black holes, regions of space where gravity has become so strong that not even light can escape. These aren't ordinary black holes. They contain the mass of millions or billions of suns crushed into regions smaller than our solar system. The gravitational forces around them are beyond human comprehension. At the center of most galaxies lurks one of these cosmic monsters. Most of the time they sit quietly, invisible against the backdrop of space, but sometimes they wake up and begin feeding. When matter falls toward a supermassive black hole, it gets compressed and heated to temperatures of millions of degrees. This creates the most efficient energy conversion process in the universe. A feeding supermassive black hole can convert matter into energy with 10% efficiency. Nuclear fusion in stars only manages 1%. This difference explains how quasars generate such impossible amounts of power. The process begins when gas and dust spiral toward the supermassive black hole. This material doesn't fall straight in. Instead, it forms a swirling disk called an accretion disk. As matter spirals inward, friction causes it to heat up dramatically. The inner regions reach temperatures of millions of degrees, hot enough to glow with intense radiation across all wavelengths of light. The accretion disk becomes a cosmic further efficient than any stellar process. Material falling into the black hole releases enormous amounts of energy as it gets compressed and accelerated. This mechanism can sustain quasar-level energy output for millions of years. As long as there's material to feed the black hole, the accretion disk continues blazing with the light of hundreds of billions of stars. The discovery of accretion disks finally explained how quasars could generate such extreme energy from such compact regions. The universe's most powerful objects were cosmic eating machines. Quasars weren't isolated objects drifting through empty space. They were the hyperactive centers of distant galaxies. The supermassive black holes powering quasars sat at the hearts of galactic communities. Scientists discovered that many galaxies have supermassive black holes at their centers. Most of the time, these black holes remain dormant, invisible against the galaxy's starlight. But when they begin actively feeding, they transform into quasars. The central black hole's accretion disk outshines the entire rest of the galaxy, making billions of stars invisible in comparison. This explained why early observations only saw point sources. The quasar's blazing central engine was so bright it completely overwhelmed the light from its host galaxy. Understanding active galactic nuclei revolutionized astronomy. These weren't alien objects. They were extreme versions of features that exist in most large galaxies, including our own. Quasars became astronomy's most powerful tools for exploring the distant universe. Their extreme brightness makes them visible across billions of light years, serving as cosmic beacons in the deep cosmos. When we observe distant quasars, we're seeing light that has traveled for billions of years to reach us. This light carries information about what the universe was like when it was much younger. Quasars act like cosmic lighthouses, illuminating the space between galaxies. Their light reveals clouds of gas and dust that would otherwise be completely invisible. By studying quasar light, astronomers can map the structure of the early universe. They can trace how matter was distributed when the cosmos was only a fraction of its current age. These cosmic monsters became our best tools for understanding how the universe evolved from its early chaotic state into the structured cosmos we see today. Looking at distant quasars is literally looking back in time. The light we see today left these objects billions of years ago, when the universe was fundamentally different. The most distant quasars show us the universe when it was less than 1 billion years old. We're seeing cosmic conditions that existed long before our solar system formed. This redshift effect makes quasars natural time machines. The farther away they are, the further back in cosmic history we're seeing. Their light preserves a record of ancient cosmic conditions. By studying quasars at different distances, astronomers can trace how the universe has changed over cosmic time. They can see how galaxies formed and evolved in the early cosmos. These objects provide direct observational evidence of cosmic evolution. They show us that the universe's most distant past was dramatically different from today. Quasars represent one of the rarest phenomena in the universe. Only about one galaxy in several thousand ever goes through an active quasar phase during its lifetime. Most supermassive black holes spend their existence in quiet dormancy. They lack sufficient material falling into them to power the extreme accretion disk activity that creates quasars. A galaxy needs specific conditions to become a quasar host. Usually this requires a major disruption, like a collision with another galaxy. That sends large amounts of gas spiraling toward the central black hole. These feeding events are temporary on cosmic timescales. A quasar might blaze for millions of years, but then fade back to dormancy as its fuel supply gets exhausted. The rarity of quasars makes them precious cosmic laboratories. They represent extreme physics in action, showing us what happens when the universe's most powerful forces operate at maximum intensity. A typical spiral galaxy contains hundreds of billions of stars. Each star blazes with nuclear fire. All those stars combined create the galaxy's total light output. Now imagine a single point source that outshines that entire galaxy. Not by a little bit, by hundreds of times. This is the reality of quasars. Individual objects no bigger than our solar system that generate more light than stellar cities containing hundreds of billions of residents. The brightness comparison defies human intuition. A quasar can outshine a galaxy containing more stars than there are grains of sand on all Earth's beaches. This makes quasars the most luminous persistent objects in the observable universe. Every energy source in the universe faces a fundamental limit. It's called the Eddington limit, named after the astronomer who discovered this cosmic speed limit for brightness. The limit works like this. As any object gets brighter, its radiation pushes outward with increasing force. Eventually, this outward radiation pressure can overpower the inward pull of gravity. When radiation pressure exceeds gravitational force, the energy source literally blows itself apart. It can't maintain the conditions needed to keep producing energy. Most stars operate far below this theoretical ceiling, but quasars push right up against the Eddington limit. They generate the maximum brightness physically possible without destroying themselves, sustained by the strongest gravitational forces in the universe. Einstein revealed that matter and energy are different forms of the same thing. His famous equation E equals mc squared shows how tiny amounts of matter can become enormous amounts of energy. The c in Einstein's equation represents the speed of light. When you square this already huge number, you get something almost incomprehensibly large. This means even small amounts of matter contain incredible energy potential. A single paperclip contains enough energy to power a city for months if you could convert it completely. Quasars achieve mass-energy conversion on cosmic scales. They transform the equivalent of several suns' worth of matter into pure energy every year, creating their impossible brightness through the most efficient energy conversion process in the universe. Nuclear fusion powers every star in the universe. It converts about 1% of matter's mass into energy. Scientists long considered this the ultimate efficiency limit for cosmic energy production. Gravitational energy conversion works completely differently. When matter falls into a supermassive black hole, gravitational forces can convert up to 10% of the matter's mass directly into energy. This tenfold efficiency advantage explains quasars' impossible energy output. They operate on a completely different level than stellar nuclear processes. The gravitational energy released by matter falling into a black hole surpasses fusion efficiency by a factor of 100. This dramatic difference allows quasars to generate galaxy-level brightness from regions smaller than planetary orbits. Quasars need constant feeding to maintain their extreme energy output. The supermassive black holes powering them consume material at tremendous rates. Gas clouds provide the primary fuel. These vast reservoirs of hydrogen and helium stretch across space, containing the mass of millions of stars. Entire stars can also fall into the feeding zone when a star ventures too close to the black hole. Gravitational forces tear it apart and add its material to the energy-producing accretion disk. The continuous supply of infalling matter sustains quasar activity for millions of years. As long as material keeps flowing toward the central black hole, the cosmic furnace continues blazing with the light of hundreds of billions of stars. Most cosmic objects emit light in limited ranges of the electromagnetic spectrum. Stars favor certain colors based on their temperature. Galaxies emit mostly visible and infrared light. Quasars break this pattern completely. They blaze across every wavelength scientists can detect. Radio waves pour from their jets. Infrared radiation streams from heated dust. Visible light blazes from the accretion disk. Ultraviolet and X-rays emerge from the hottest regions near the black hole. This broad-spectrum emission creates quasars' distinctive signature. No other cosmic objects produce such intense radiation across the entire electromagnetic spectrum, making them instantly recognizable to astronomers studying any wavelength of light. Imagine traveling to a quasar's neighborhood. Your spacecraft approaches to the same distance Earth orbits from our Sun. From this vantage point, the quasar's accretion disk would appear tens of thousands of times brighter than our Sun appears from Earth. The blazing disk would fill your view with light intense enough to vaporize any normal material. The energy density would be beyond human comprehension. Every square meter of space would be flooded with more radiation than the entire output of typical stars. This thought experiment reveals quasars' true energy scales. Objects that appear as faint dots in our most powerful telescopes are actually blazing with brightness that would overwhelm any observer who ventured within their immediate cosmic neighborhood. Quasars exist at distances that strain human imagination. The light we see today began its journey billions of years ago, when the universe was fundamentally younger. These vast distances create a cosmic paradox. Objects generating more energy than entire galaxies appear as faint points of light in our telescopes. Space itself dilutes their incredible brightness, the same way a flashlight grows dimmer with distance. Quasar light spreads out over cosmic distances until only a tiny fraction reaches Earth. Yet even this tiny fraction is enough for us to detect them across billions of light years. This reveals just how staggeringly bright quasars must be at their source to remain visible across such enormous cosmic distances. Different parts of a quasar's accretion disk reach wildly different temperatures. Scientists measure these temperatures by analyzing the colors of light different regions emit. The outer edges of the accretion disk glow at tens of thousands of degrees, hot enough to vaporize any Earth material, but relatively cool by quasar standards. Moving inward, temperatures climb rapidly. The inner regions near the black hole reach millions of degrees. These zones emit intense X-rays and ultraviolet radiation. The temperature gradient spans from merely star-hot to plasma conditions that exceed the cores of the most massive stars. This range of extreme temperatures across a single object creates quasars' complex multi-wavelength emissions and contributes to their record-breaking energy output. Our sun will shine for about 10 billion years. Over its entire lifetime, it will convert roughly 1% of its mass into energy through nuclear fusion. A typical quasar produces this same amount of energy in mere seconds. Every few seconds, it generates the equivalent of our sun's entire lifetime energy output. This energy budget operates on scales that reduce stellar processes to cosmic insignificance. Quasars demonstrate energy production that makes even the largest stars seem dim by comparison. The numbers reveal just how extreme these objects are. In the time it takes you to read this sentence, a bright quasar has produced more energy than our sun will generate in millions of years. Nothing can escape from inside a black hole. Not matter, not energy, not even light itself. This absolute prison is defined by an invisible boundary called the event horizon. The event horizon isn't a physical surface. It's a mathematical boundary in space-time where the escape velocity equals the speed of light. Think of it like a cosmic waterfall. Once you go over the edge, there's no way to swim back upstream. The current becomes too powerful for any force to overcome. For supermassive black holes, this boundary can span regions larger than planetary orbits. Yet it remains completely invisible from the outside. The event horizon marks the ultimate limit of what we can observe about these cosmic monsters. At the very center of every black hole lies something that defies human understanding. Physicists call it a singularity, a point where density becomes infinite and the normal rules of reality cease to apply. Our best theories predict that all the black hole's mass gets crushed into a single point with no size at all. The gravitational forces become so extreme that space and time themselves break down. No known physical laws can describe what happens at a singularity. Einstein's relativity and quantum mechanics both fail when densities reach infinite values. This breakdown of physics occurs at the heart of every quasar's central engine. The singularity creates gravitational fields so powerful they can transform ordinary matter into the universe's most efficient energy source. Matter falling toward a black hole cannot simply plunge straight inward. Physics prevents this direct collision through a fundamental principle called conservation of angular momentum. Angular momentum is like cosmic spin. Just as figure skaters spin faster when they pull their arms inward, infalling matter speeds up as it approaches the black hole. This spinning motion forces the material into a swirling disk structure. The matter spirals inward like water going down a cosmic drain, forming what astronomers call an accretion disk. These disks can stretch across regions larger than our entire solar system. They become the primary components of quasar engines, transforming gravitational energy into the blazing light we observe across cosmic distances. Different parts of the accretion disk orbit at different speeds. Material closer to the black hole moves much faster than material farther away. This creates intense friction between neighboring regions of the disk. Friction converts orbital motion into heat. The same process that warms your hands when you rub them together operates on cosmic scales within accretion disks. As material spirals inward, friction heats it to temperatures of millions of degrees. These temperatures exceed those found in stellar cores, creating plasma conditions that glow across all wavelengths of light. The friction heating mechanism transforms the gravitational energy of infalling matter into thermal energy. This thermal energy then radiates away as the intense light that makes quasars visible across billions of light years. Accretion disks don't rotate like solid wheels. Instead, they follow Kepler's laws of orbital motion, with inner regions completing orbits much faster than outer regions. This differential rotation is similar to how planets move around the Sun. Mercury races around its orbit in just 88 days, while distant Pluto takes 248 years to complete one circuit. In accretion disks, this speed difference creates shearing forces that stretch and twist magnetic field lines. The effect is like wringing out a cosmic towel, building up enormous magnetic energy. These twisted magnetic fields become crucial for channeling matter inward and sometimes launching powerful jets outward. Differential rotation transforms simple orbital motion into complex magnetic dynamics that control the entire quasar engine. Material in accretion disks faces a fundamental problem. Angular momentum conservation should keep it orbiting forever at the same distance from the black hole. Yet somehow matter must lose angular momentum to spiral inward and feed the central engine. The solution comes from turbulent processes that create viscosity within the disk. Turbulence transfers angular momentum from inner regions to outer regions, allowing inner material to fall inward. Magnetic fields play a crucial role in this process. They create magnetorotational instabilities that generate turbulence throughout the disk structure. This viscous transport mechanism solves the angular momentum problem. It allows steady inflow of matter toward the black hole while simultaneously spreading the disk material outward, creating the sustained feeding that powers quasar activity. Even in the extreme environment near a black hole, there exists a last stable parking orbit. Astronomers call this the innermost stable circular orbit, or ISCO for short. Material can maintain circular orbits outside this boundary, but inside the ISCO, stable circular motion becomes impossible. The black hole's gravity overwhelms any attempt to maintain a circular path. For typical supermassive black holes, the ISCO sits at about 3 times the event horizon radius. This creates a gap between the inner edge of the accretion disk and the point of no return. Material crossing the ESCO begins its final death spiral into the black hole. This transition zone marks where the orderly accretion disk structure breaks down and matter begins its ultimate journey toward the singularity. Photons climbing out of strong gravitational fields lose energy in the process. This energy loss causes their wavelengths to stretch toward the red end of the spectrum, creating gravitational redshift. The effect is similar to how sound from a receding ambulance shifts to lower pitch. But gravitational redshift happens to light escaping from regions of intense gravity. Light emitted from the inner accretion disk suffers severe gravitational redshift as it climbs out of the black hole's gravity well. This shifts the apparent colors and reduces the apparent brightness of radiation from the hottest regions. Gravitational redshift becomes extreme near event horizons. Light from just outside the event horizon gets redshifted so severely that it becomes virtually undetectable to distant observers, creating the black hole's characteristic darkness. Strong gravitational fields don't just bend space, they also warp time itself. Clocks run slower in regions of intense gravity compared to areas with weaker gravitational fields. This effect, called gravitational time dilation, becomes extreme near black holes. Time passes much more slowly for matter in the inner accretion disk than for observers at large distances. From our perspective on Earth, processes in quasar accretion disks appear to happen in slow motion. What seems like rapid changes to local matter actually unfolds over much longer timescales for distant observers. Time dilation helps explain why quasar variability appears to happen on timescales of days or weeks rather than milliseconds. The extreme gravity near supermassive black holes stretches time itself, making rapid local processes appear much slower to external observers. Accretion disks contain ionized gas that conducts electricity like cosmic copper wire. When this conducting material moves through magnetic fields, it creates powerful electromagnetic effects. The differential rotation of the disk acts like a cosmic dynamo. It stretches and twists magnetic field lines, amplifying their strength by factors of millions or billions. These amplified magnetic fields can become so strong they dominate the behavior of matter in the disk. They channel material flows, launch jets, and create the complex magnetic structures that control quasar activity. The magnetic field amplification process transforms ordinary stellar magnetic fields into the most powerful magnetic structures in the universe, creating the conditions necessary for relativistic jet formation and extreme energy output. At the extreme temperatures found in quasar accretion disks, light itself becomes a significant source of pressure. This radiation pressure pushes outward against the inward pull of gravity. In the hottest regions of the disk, radiation pressure can exceed the pressure from gas particles by factors of hundreds or thousands. The intense light field becomes the dominant influence on matter motion. This radiation pressure dominance creates a delicate balance. Too much heating in the radiation pressure blows the disk apart. Too little and gravity wins, causing rapid infall that changes the disk structure. The competition between radiation pressure and gravitational attraction helps regulate quasar energy output. This balance mechanism prevents accretion disks from either blowing themselves apart or collapsing too rapidly to sustain steady energy production. Quasar accretion disks operate near critical stability limits. When the rate of matter inflow exceeds certain threshold values, the entire disk structure can become violently unstable. These instabilities manifest as dramatic changes in brightness and energy output. A stable quasar can suddenly flare to many times its normal brightness, then fade back to quiescence over periods of months or years. The instabilities arise from the complex interplay between gravity, magnetic fields, and radiation pressure. Small perturbations can cascade into major disruptions that reorganize the entire disk structure. These threshold effects explain why quasars show such dramatic variability in their light output. The accretion process operates so close to stability limits that minor changes in feeding rate can trigger major changes in observable properties. Some quasars don't just shine brilliantly. They also fire narrow beams of material into space at speeds approaching the ultimate cosmic speed limit. These jets emerge from the polar regions of spinning supermassive black holes. The combination of rapid rotation and powerful magnetic fields creates cosmic particle accelerators more efficient than anything humans have ever built. The jets stretch across distances that dwarf entire galaxy clusters. Material launched from regions smaller than our solar system travels for millions of light years before finally slowing down. Jet formation requires precise conditions that align the black hole's rotation axis with twisted magnetic field lines. When these elements combine perfectly, they create the universe's most spectacular displays of directed energy release. Rotating black holes possess enormous amounts of rotational energy stored in their spin. For decades, physicists wondered if this energy could ever be extracted and used. The answer came from theoretical work by Roger Blandford and Roman Znajek. They discovered that magnetic field lines threading through the black hole's ergosphere can tap directly into the rotation energy. The ergosphere is a region just outside the event horizon where spacetime itself gets dragged around by the black hole's spin. Magnetic fields in this region get twisted and wound up like cosmic springs. This twisting process extracts rotational energy from the black hole and channels it along the magnetic field lines. The Blandford-Znajek mechanism transforms black hole spin into the kinetic energy that powers relativistic jets. But jet material doesn't gradually build up speed like a car accelerating on a highway. Instead, it gets almost instantly to velocities approaching the speed of light. These speeds represent 99% or more of light's velocity. At such extreme speeds, the normal rules of motion break down and Einstein's special relativity takes over. Nothing with mass can actually reach the speed of light. But quasar jets push matter closer to this ultimate speed limit than almost any other natural process in the universe. The near-light speed acceleration happens over relatively short distances near the black hole. Magnetic field acceleration is so efficient that particles reach relativistic velocities within just a few times the black hole's event horizon radius. When objects approach light speed, they experience effects that seem impossible by everyday standards. Time slows down, distances contract, mass appears to increase. These relativistic effects are quantified by something called the Lorentz factor. For typical quasar jets, the Lorentz factor reaches values of 10 to 100. This means time passes 10 to 100 times slower for jet material compared to stationary observers. A process that takes 1 second in the jet's reference frame appears to take minutes or hours from our perspective on Earth. This time dilation effect dramatically alters how we observe jet behavior. The extreme Lorentz factors in quasar jets create some of the most relativistic environments in the natural universe. They serve as cosmic laboratories for testing Einstein's theories under conditions impossible to recreate on Earth. Jets pointed nearly toward Earth create one of astronomy's most mind-bending optical illusions. The combination of near-light speed motion and special relativity makes jet material appear to move faster than light itself. This apparent faster-than-light motion is called superluminal motion. It's not real motion faster than light, but rather a projection effect combined with relativistic time delays. Light from different parts of the jet reaches us at slightly different times because of the jet's high-speed approach toward Earth. When we string these arrival times together, the jet appears to cover distances faster than light could travel. Doppler boosting also makes approaching jets appear dramatically brighter than they actually are. Jets aimed toward Earth can appear hundreds of times brighter than identical jets pointed in other directions. Early observations of quasar jets revealed material that seemed to violate Einstein's cosmic speed limit. Astronomers measured jet components moving at apparent speeds of several times the velocity of light. This apparent superluminal motion initially caused tremendous confusion. Scientists knew that nothing could actually exceed light speed, yet the observations seemed to show exactly that happening. The resolution came from understanding projection effects in relativistic motion. When jets move at near light speed toward Earth, their projected motion across the sky can appear faster than light. The apparent superluminal motion becomes an important diagnostic tool. It allows astronomers to determine jet speeds and orientations, even when the jets are too distant to resolve their detailed structure. Relativistic electrons in jet magnetic fields don't travel in straight lines. Instead, they spiral around magnetic field lines in helical paths that emit distinctive radiation. This synchrotron radiation spans wavelengths from radio waves to X-rays. The same emission mechanism that creates radio static also produces the high-energy radiation that makes jets visible across the entire electromagnetic spectrum. The synchrotron process is incredibly efficient at converting electron kinetic energy into electromagnetic radiation. This efficiency makes jets visible across cosmic distances despite their relatively narrow beam width. Different electron energies produce different radiation wavelengths. Radio observations reveal lower energy electrons, while X-ray observations detect the highest energy particles accelerated to extreme speeds within the jets. High-energy electrons in quasar jets don't just emit synchrotron radiation, they also interact with existing photons, boosting low-energy light to much higher energies through a process called inverse Compton scattering. When a high-speed electron collides with a photon, it can transfer some of its energy to that photon. This collision boosts the photon from low-energy radio or optical wavelengths up to high-energy gamma rays. The gamma rays produced by inverse Compton scattering make some quasar jets detectable by space-based gamma-ray telescopes. These observations reveal the highest energy processes occurring within the jets. This scattering mechanism provides another way for jets to convert particle energy into electromagnetic radiation, contributing to their broad spectrum emission and helping make them visible across billions of light years. Relativistic jets don't travel through empty space. They plow through the gas and dust that fills the regions between galaxies, creating spectacular collision zones. When jets slam into this intervening material, they create shock waves that heat gas to millions of degrees. These collision zones light up like cosmic fireworks, creating bright hotspots at the ends of radio jets. The interactions also slow down the jet material and spread it out into larger structures called radio lobes. These lobes can extend for millions of light years on either side of the central quasar. Jet-medium interactions serve as cosmic laboratories for studying shock physics under extreme conditions. They create some of the largest and most energetic structures associated with individual galaxies. Light waves normally vibrate in all directions perpendicular to their travel direction. But synchrotron radiation from jets becomes polarized, meaning the light waves vibrate preferentially in specific directions. This polarization provides crucial information about magnetic field orientations within the jets. The direction of polarization directly reflects the alignment of magnetic field lines. Polarization measurements reveal that jets contain highly organized magnetic field structures. These fields remain aligned across enormous distances, indicating powerful forces that maintain jet coherence. The degree of polarization can reach levels of 10 to 20%, much higher than typical astronomical sources. This high polarization serves as a signature of the organized magnetic fields that guide and focus relativistic jet material. Quasar jets don't maintain constant brightness. They flicker and vary on timescales ranging from hours to years, revealing the chaotic internal processes that drive jet activity. These brightness variations often show complex patterns. Multiple bright knots of material travel down the jets at different speeds, creating interference patterns as they overtake and interact with each other. Rapid variability indicates that jet acceleration and particle injection happen in discrete episodes rather than as steady continuous processes. The jets experience periodic bursts of activity triggered by instabilities in the accretion disk. The variability patterns serve as probes of jet internal structure. By tracking how disturbances propagate down the jets, astronomers can map the changing conditions within these relativistic outflows, how black hole activity connects to large-scale jet behavior. Every supermassive black hole started small. The cosmic monsters powering today's quasars began as much smaller objects called seed black holes in the early universe. These primordial seeds formed through several possible pathways. Some emerged from the collapse of the first generation of massive stars. Others condensed directly from dense gas clouds without ever forming stars. The seed formation process happened when the universe was much younger and denser than today. Conditions in the early cosmos favored rapid black hole formation from available matter concentrations. Once formed, these seed black holes became the foundation for all future quasar activity. Every blazing quasar we observe today traces its origins back to these modest beginnings in cosmic dawn, when the universe was still assembling its first large-scale structures. Seed black holes don't remain small for long under the right feeding conditions. When sufficient material becomes available, they can grow at rates that defy human intuition. The growth follows exponential mathematics rather than simple addition. Each bit of matter that falls in increases the black hole's gravitational pull, which helps it capture even more material. This runaway process can transform modest, seed black holes into billion solar mass giants in relatively short cosmic time periods. The exponential nature means growth accelerates dramatically once it begins. The rapid expansion explains how supermassive black holes reached enormous sizes so early in cosmic history. Exponential growth operating near theoretical efficiency limits can create quasar, powering black holes faster than most other astronomical processes. Quasars cannot maintain their extreme energy output indefinitely. Eventually, They exhaust the gas reservoirs that feed their central black holes, causing their brilliant activity to fade. The fuel depletion happens through several mechanisms. Nearby gas gets consumed by the accretion process. More distant material gets heated and blown away by the quasar's own energy output. Some gas reservoirs simply get disrupted by galactic dynamics. Gravitational interactions can redirect material away from the black hole's feeding zone, cutting off the supply chain. When fuel supplies dwindle below critical thresholds, quasar activity drops dramatically. The cosmic monster enters a starvation phase where it can no longer sustain the accretion disk activity needed for brilliant energy output across cosmic distances. Quasars carry the seeds of their own destruction. The intense energy they produce eventually disrupts the very conditions that allow them to exist. Strong radiation pressure pushes against infalling matter. Powerful jets heat surrounding gas to temperatures too high for efficient cooling and accretion. This self-limiting behavior creates a natural regulation mechanism. The more energy a quasar produces, the more effectively it destroys its own feeding environment. The feedback process explains why quasar activity is typically temporary rather than permanent. These cosmic engines automatically shut themselves down when their energy output becomes so intense that it overwhelms the gravitational forces trying to deliver fuel to the central black hole. Most quasars don't shine continuously throughout cosmic history. Instead, they flicker on and off in cycles that can span millions of years between active phases. These duty cycles depend on the irregular supply of material to the central black hole. Galaxy mergers or gravitational disruptions periodically deliver new fuel loads to previously dormant systems. A single supermassive black hole might experience multiple quasar episodes during its lifetime. Each feeding event can reignite the cosmic engine for periods ranging from millions to hundreds of millions of years. The intermittent nature means that many more galaxies have experienced quasar phases than we currently observe as active. The duty cycle pattern multiplies the total number of galaxies that have hosted these cosmic monsters throughout their evolutionary histories. Quasar activation doesn't happen randomly. Specific environmental conditions must align to trigger the transition from dormant black hole to blazing cosmic engine. Galaxy mergers provide the most dramatic trigger mechanism. When two galaxies collide, their gravitational interaction funnels gas toward the central regions where supermassive black holes reside. Less violent processes can also initiate quasar activity. Cooling flows, bar instabilities, and interactions with nearby galaxies can all deliver material to previously starved black holes. The environmental dependency explains why quasar activity correlates with cosmic density. Regions with more galaxies and ongoing interactions show higher rates of quasar activation than isolated cosmic environments where gravitational triggers remain absent. The universe contained far more active quasars in the past than it does today. This cosmic evolution reflects fundamental changes in galaxy formation and gas availability over billions of years. Peak quasar activity occurred when the universe was roughly 1/4 of its current age. During this cosmic epoch, galaxy mergers were more common and gas reservoirs were more abundant. As the universe expanded and evolved, conditions became less favorable for sustained quasar activity. Gas got consumed by star formation or dispersed by previous quasar episodes. The evolutionary trend means we live in a relatively quiet cosmic era compared to the universe's more turbulent past. Today's rare active quasars are remnants of a time when such extreme activity was far more common throughout cosmic space. Astronomers study quasar populations by measuring how many objects exist at each brightness level. This distribution, called the luminosity function, reveals important patterns about quasar demographics. The brightest quasars are extremely rare. For every ultra-luminous quasar, that outshines hundreds of galaxies. Thousands of dimmer objects operate at more modest energy levels. This brightness pattern follows a steep power law relationship. Small increases in brightness correspond to dramatic decreases in the number of objects at that brightness level. The luminosity function shape reflects the fundamental physics of black hole feeding and growth. The rarity of extremely bright quasars indicates that the conditions needed for maximum energy output occur only under exceptional circumstances in cosmic evolution. Most supermassive black holes in the present-day universe remain dormant. They lurk invisibly at galactic centers, no longer producing the brilliant emissions that would classify them as active quasars. These sleeping giants retain their enormous mass and gravitational influence. They continue to affect stellar orbits and galactic dynamics even without active accretion disks. The dormant black holes represent quasars in their retirement phase. They've exhausted nearby fuel supplies and lack the environmental triggers needed to reignite sustained activity. Dormant phases can persist for billions of years, potentially lasting longer than the active quasar periods. The quiet giants greatly outnumber currently active quasars, creating a vast hidden population of cosmic monsters waiting in galactic centers throughout the universe. Dormant supermassive black holes can return to quasar activity under the right circumstances. These reactivation events transform quiet galactic centers back into blazing cosmic engines. New fuel delivery provides the key to reactivation. Galaxy interactions, mergers, or changes in gas dynamics can redirect material toward previously starved black holes. The reactivation process can happen multiple times during a black hole's lifetime. Some systems alternate between active and dormant phases over billions of years of cosmic evolution. Recent observations have detected galaxies in the process of transitioning from dormant to active states. These reactivation events demonstrate that quasar evolution is not a one-way process, but rather a complex cycle that can repeat whenever environmental conditions provide sufficient fuel for renewed cosmic monster activity. Astronomers discovered something unexpected when they measured both black hole masses and the properties of their host galaxies. A tight correlation emerged that nobody had predicted. The relationship connects the mass of central supermassive black holes to the orbital speeds of stars in the galaxy's central bulge. This bulge is the dense, spherical region of old stars that forms the galaxy's core. When stars move faster in the galactic center, the central black hole invariably turns out to be more massive. The correlation is so precise that astronomers can predict black hole mass just by measuring stellar velocities. This M-sigma relationship suggests that black holes and galaxies don't grow independently. Instead, they must influence each other's development through processes that operate over billions of years, creating one of astronomy's most fundamental scaling laws. Galaxies and their central black holes grow together like cosmic dance partners. Neither develops in isolation. Each influences the other's growth through a complex feedback relationship. When galaxies accumulate more mass through mergers and gas accretion, they also feed more material to their central black holes. The black holes grow larger and become more active. More active black holes then affect their host galaxies through energy output in jets. This creates a self-regulating system where galaxy properties and black hole properties remain linked. The coevolution process explains why massive galaxies always contain massive black holes, while smaller galaxies host smaller black holes. This cosmic partnership has operated throughout the universe's history, shaping both galaxy formation and black hole demographics. Active quasars don't just consume material and produce energy. They also act as cosmic thermostats that regulate star formation throughout their host galaxies. When quasars reach peak activity, they pump enormous amounts of energy into the surrounding gas. This energy heats gas clouds to temperatures too high for gravitational collapse and star formation. Hot gas cannot cool efficiently enough to condense into new stars. The quasar's energy output effectively shuts down the galaxy's ability to form new stellar generations. This negative feedback mechanism prevents galaxies from converting all their gas into stars too quickly. Without this regulation, massive galaxies would exhaust their star-forming material in just a few 100 million years, creating a universe filled with dead galactic systems. Quasar activity doesn't always shut down star formation. Under certain conditions, jets and outflows from active black holes can actually trigger new waves of stellar birth. When jets plow through surrounding gas clouds, they create shock waves that compress the material. This compression can push gas densities above the threshold needed for gravitational collapse. The compressed gas forms new stars at accelerated rates. Regions that might have taken millions of years to form stars can suddenly burst into activity within just thousands of years. This positive feedback creates a complex relationship between quasar activity and galaxy evolution. The same black hole that eventually shuts down star formation may first trigger intense periods of stellar birth, fundamentally altering the galaxy's structure and composition. Central supermassive black holes need constant feeding to maintain quasar-level activity. But galaxy-scale distances present a fundamental challenge for delivering material to such tiny central regions. Galaxy mergers provide one solution to this feeding problem. When two galaxies collide, gravitational torques funnel gas from the outer regions toward the combined galactic center. Cooling flows offer another pathway for gas delivery. In some galaxies, hot gas gradually cools and flows inward under its own gravity, creating steady streams of material that can feed central black holes. These inflow channels solve the angular momentum problem that normally prevents material from reaching black hole feeding zones. They create the conditions necessary for sustained quasar activity by establishing direct pathways from galaxy-scale gas reservoirs to black hole-scale accretion regions. Many spiral galaxies develop elongated bar structures that stretch across their central regions. These bars aren't just decorative features. They function as efficient transport mechanisms for moving gas inward. The bar's gravitational field creates non-circular orbits for gas clouds. Instead of maintaining stable circular orbits, gas gets channeled along spiral paths that lead toward the galactic center. This transport mechanism can deliver material from distances of thousands of light years directly to the black hole's feeding zone. The bar acts like a cosmic conveyor belt, solving the angular momentum problem through gravitational engineering. Galaxies with prominent bars show enhanced central activity compared to galaxies without bars. The bar structure provides a direct link between galaxy-scale gas reservoirs and black hole-scale feeding, explaining why many active galaxies display distinctive bar morphology. Black holes cannot grow indefinitely. Eventually, they reach sizes where their own energy output prevents further feeding, creating a self-limiting growth mechanism. As black holes become more massive, their quasar activity intensifies. The increased energy output heats and disperses the surrounding gas that would otherwise fall into the black hole. Strong radiation pressure and powerful jets blow away potential fuel before it can reach the accretion disk. The black hole essentially cuts off its own food supply through excessive energy production. This termination mechanism explains why supermassive black holes reach maximum sizes of a few billion solar masses rather than growing without limit. The self-regulation process creates a natural ceiling for black hole growth that depends on the balance between gravitational attraction and radiation pressure. A quasar activity dramatically accelerates the chemical evolution of galaxy interiors. The intense energy output and powerful jets distribute heavy elements throughout galactic volumes much faster than normal stellar processes. Jets carry material enriched with elements created in previous stellar generations. As these jets interact with surrounding gas, they seed new regions with metals necessary for planet formation. The turbulence created by quasar activity also mixes different gas populations within galaxies. Material from various locations gets stirred together, homogenizing the chemical composition across large galactic volumes. This accelerated chemical evolution helps explain why galaxies that experienced early quasar phases show more uniform elemental compositions than galaxies that remained quiescent. Quasar activity acts as a cosmic mixing mechanism that spreads heavy elements throughout galactic systems. Quasar activity can fundamentally alter the structural appearance of entire galaxies. The intense energy output and mechanical effects reshape galactic architecture over cosmic time. Many spiral galaxies that host powerful quasars eventually transform into elliptical galaxies. The quasar activity disrupts the delicate balance needed to maintain spiral arm structure. Gas gets heated and expelled from the galactic disk, removing the material needed to sustain star formation in spiral patterns. Without ongoing star formation, spiral arms fade and disappear. The final result is a smooth, elliptical galaxy populated mainly by older stars. This morphological transformation represents one of the most dramatic ways that black hole activity can reshape its cosmic environment, changing the fundamental character of galactic systems. Astronomers observe a distinct population of galaxies that appear red in color and show little ongoing star formation. These galaxies form what's called the red sequence, a cosmic cemetery of systems that have exhausted their star-forming potential. The red coloration comes from older stellar populations. When star formation stops, the bright blue light from young massive stars disappears, leaving only the redder light from long-lived smaller stars. Many red sequence galaxies show evidence of past quasar activity. The correlation suggests that quasar phases play a crucial role in transforming active, star-forming galaxies into passive, red systems. The red sequence represents the endpoint of galaxy evolution. Systems that have completed their star formation and settled into quiet old age. Quasar activity appears to be the primary mechanism that drives galaxies from active youth to passive maturity. Galaxy evolution follows a pattern that contradicts human intuition about how cosmic structures should develop. Larger, more massive galaxies actually complete their evolution earlier than smaller systems. This downsizing effect means that the biggest galaxies in the universe finished forming new stars billions of years ago, while smaller galaxies continue active star formation today. The pattern emerges because massive galaxies also host the most massive black holes. These powerful black holes reach quasar activity levels earlier and shut down star formation more efficiently than their smaller counterparts. Downsizing reveals the crucial role that black hole mass plays in determining galaxy evolutionary timescales. The most massive systems burn bright and fast, then fade to red quiescence, while smaller galaxies take billions of years longer to exhaust their star-forming potential. Quasar light contains distinctive fingerprints that immediately reveal their identity to astronomers. These fingerprints appear as bright emission lines in their spectra. A spectrum splits quasar light into its component colors, like a prism creating a rainbow. Within this cosmic rainbow, certain wavelengths shine much brighter than others, creating the characteristic emission line signatures. The strongest lines come from hydrogen and carbon atoms energized by the quasar's intense radiation. These atoms absorb energy from the blazing accretion disk, then re-emit it at specific wavelengths. The emission lines also appear unusually broad compared to typical stellar spectra. This broadening comes from the extreme velocities of gas swirling around the supermassive black hole, creating the unmistakable spectroscopic signature that identifies quasar activity across cosmic distances. Between Earth and distant quasars lies a cosmic obstacle course of hydrogen clouds. These clouds leave their mark on quasar light by absorbing specific wavelengths during the photon's billion-year journey through space. The absorption creates what astronomers call the limit alpha forest. This forest consists of hundreds of narrow absorption lines that appear at different wavelengths in quasar spectra. Each absorption line represents an individual hydrogen cloud along the line of sight. Denser clouds create stronger absorption features, while thinner clouds produce weaker signatures. The Lyman alpha forest transforms every quasar into a probe of intergalactic space structure. By analyzing the pattern and strength of absorption lines, astronomers can map the three-dimensional distribution of matter between galaxies across billions of light years. Light waves normally vibrate in all directions perpendicular to their travel path. But under certain conditions, these vibrations become aligned in preferred directions, creating polarized light. Quasar light often shows significant polarization levels that reveal important information about magnetic field structures. The degree and direction of polarization directly reflect the organization of magnetic fields within quasar jets and accretion disks. Polarization measurements require specialized instruments that can detect the alignment of light wave vibrations. These observations are technically challenging but provide unique insights unavailable through normal brightness measurements. The polarization data reveals that quasars contain highly organized magnetic field systems extending across enormous distances. This magnetic architecture plays a crucial role in channeling energy flows and directing relativistic jets, making polarization studies essential for understanding quasar physics. Single wavelength observations provide only partial pictures of quasar activity. To understand these complex objects fully, astronomers coordinate observations across the entire electromagnetic spectrum. These multi-wavelength campaigns involve telescopes that detect radio waves, infrared radiation, visible light, ultraviolet emissions, X-rays, and gamma rays simultaneously. Each wavelength range reveals different physical processes within the quasar. The coordinated observations must happen at the same time because quasars vary their brightness unpredictably. Changes in one wavelength often correspond to changes in others, but only simultaneous measurements can reveal these correlations. Multi-wavelength studies create comprehensive energy portraits that show how different quasar components interact with each other. These complete pictures are essential for developing accurate theoretical models of how supermassive black holes convert matter into energy across cosmic scales. Not all quasars appear identical in their spectroscopic signatures. Astronomers classify them into different types based on which spectral features are visible in their light. Type 1 quasars show both broad and narrow emission lines in their spectra. The broad lines come from gas moving at high speeds very close to the central black hole, while narrow lines originate from more distant, slower-moving material. These objects provide direct views of the innermost regions around supermassive black holes. The broad emission lines require gas velocities of thousands of kilometers per second, indicating material orbiting extremely close to the event horizon. Type 1 quasars represent the clearest examples of unobscured active galactic nuclei. Their spectra contain the most complete information about physical conditions near supermassive black holes, making them ideal laboratories for studying extreme gravitational environments. Some quasars appear fundamentally different in their spectral properties. Type 2 quasars show only narrow emission lines, with the characteristic broad lines completely absent from their spectra. The missing broad lines don't mean these objects lack high-velocity gas near their central black holes. Instead, thick dust clouds block our direct view of the innermost regions where broad line emission originates. This dust forms a torus-shaped structure that surrounds the accretion disk. When we view the quasar through this dusty torus, it absorbs the broad line emission while allowing narrow lines from more distant regions to reach us. Type 2 quasars demonstrate that orientation effects significantly influence how we observe these objects. The same physical processes operate in both Type 1 and Type 2 systems, but cosmic dust determines which spectral features we can detect from Earth. Not every active supermassive black hole reaches full quasar brightness levels. Many galaxies host central black holes that show activity signatures but generate much less energy than classic quasars. These lower luminosity objects include categories called LNRs and Seyfert galaxies. LNR stands for Low Ionization Nuclear Emission Region, while Seyfert galaxies represent an intermediate activity level between normal galaxies and full quasars. The weaker activity results from reduced accretion rates onto the central black holes. These objects consume matter more slowly than quasars, producing proportionally less energy output and different ionization conditions in surrounding gas. LNR and Seyfert galaxies are much more common than luminous quasars, representing the typical level of supermassive black hole activity in the present-day universe. They show that quasar-like processes operate across a wide range of energy scales in galactic centers. Some quasars appear extraordinarily bright and variable compared to typical objects at similar distances. These extreme examples belong to a special category called blazars. Blazars represent quasars whose relativistic jets point almost directly toward Earth. This orientation creates dramatic observational effects due to relativistic beaming and Doppler boosting of the jet emission. The near-perfect alignment between jet direction and our line of sight makes blazar jets appear much brighter than they would from other viewing angles. The objects can vary dramatically in brightness over periods of days or even hours. Blazar observations provide the clearest views of relativistic jet physics because we're looking straight down the barrel of these cosmic particle accelerators. Their extreme variability and brightness make them ideal natural laboratories for studying matter moving at near-light speeds. Quasars split into two distinct populations based on their radio emission properties. This fundamental division reveals important differences in how these objects channel their energy output. Radio-loud quasars produce powerful jets that emit intense radio radiation extending far beyond their host galaxies. These jets create enormous radio lobes that can span millions of light-years. Radio-quiet quasars generate much weaker radio emissions and lack the extended jet structures seen in radio-loud systems. Their energy output focuses primarily on thermal emission from accretion disks rather than jet production. The radio dichotomy appears to correlate with other quasar properties, including host galaxy type and black hole spin rates. This division suggests that different physical mechanisms control energy conversion in these two quasar populations, with jet production depending on specific conditions near the central black hole. Some quasars show unusual spectral signatures that initially puzzled astronomers. Instead of the typical emission lines, these objects display broad absorption troghs that span significant wavelength ranges. These broad absorption line quasars, or BL quasars, contain high-velocity outflows that absorb light from the central engine. The outflowing material creates the distinctive broad absorption features in their spectra. The absorption lines indicate gas moving away from us at speeds reaching 20,000 kilometers per second. This represents some of the fastest non-relativistic outflows detected in astronomical objects. But Bell quasars demonstrate that not all material near supermassive black holes falls inward toward the event horizon. Powerful radiation pressure and magnetic forces can launch substantial amounts of matter back into intergalactic space, revealing the complex dynamics of quasar feeding and feedback processes. Sometimes astronomers discover what appears to be multiple quasars clustered together in the same region of sky, but detailed observations reveal these are actually multiple images of single, more distant objects. Gravitational lensing creates these multiple images when a massive galaxy lies directly between Earth and a background quasar. The galaxy's gravity bends the quasar's light rays, creating several different light paths to our telescopes. Each lensed image shows the same quasar from a slightly different light travel time. This creates opportunities to study quasar variability and measure cosmic distances through time delay observations. Gravitational lensing transforms foreground galaxies into natural telescopes that magnify and multiply distant quasar images. These cosmic magnifying glasses allow detailed study of objects that would otherwise be too faint to analyze with current astronomical instruments. Individual stars within lensing galaxies create additional subtle effects on multiply-imaged quasars. These microlensing events provide unique probes of quasar structure on scales impossible to resolve directly. When stars in the lensing galaxy move across the line of sight to different parts of the quasar, they create small but measurable brightness changes in the lensed images. Different quasar components respond differently to microlensing effects. The compact accretion disk shows stronger microlensing variations than more extended emission regions. Microlensing studies reveal that quasar accretion disks are indeed extremely compact, confirming theoretical predictions about their physical sizes. This technique provides the only direct method for measuring the actual dimensions of quasar energy-producing regions across cosmic distances. Astronomers need reliable distance markers to map the universe's structure. Objects with known brightness serve as cosmic measuring sticks called standard candles. Quasars can function as standardized distance indicators through their consistent relationships between different properties. When astronomers measure certain spectral features, they can predict the quasar's intrinsic brightness. This standardization works because quasar physics follows predictable patterns. The relationship between accretion disk temperature and total energy output remains remarkably consistent across cosmic time. Using quasars as standard candles allows distance measurements to the universe's most remote regions. These cosmic lighthouses extend our distance measuring capabilities far beyond what traditional stellar methods can achieve, enabling precise mapping of cosmic expansion history. The early universe underwent a fundamental phase transition that changed its basic character. Initially, space was filled with neutral hydrogen atoms that absorbed most ultraviolet light. This cosmic dark age ended when the first stars and quasars began shining. Their intense radiation gradually ionized the neutral hydrogen, making space transparent to ultraviolet light once again. Quasar spectra preserve a record of this reionization process. Light from distant quasars encounters neutral hydrogen clouds along its journey to Earth, creating distinctive absorption features. By studying quasars at different distances, astronomers can trace how reionization progressed through cosmic time. The most distant quasars show us the universe when reionization was still incomplete, revealing the transition from cosmic darkness to transparency. Some of the universe's first galaxies remain too faint to detect directly with current telescopes, but quasar illumination can reveal their presence through glowing hydrogen signatures. These early galaxies contain vast amounts of neutral hydrogen gas. When intense quasar radiation hits this gas, it causes the hydrogen to fluoresce with distinctive light called Lyman alpha emission. The glowing hydrogen creates enormous luminous blobs around distant quasars. These Lyman alpha blobs can extend for hundreds of thousands of light years, making them visible even when the galaxies themselves remain undetectable. This fluorescence technique transforms quasars into cosmic searchlights that illuminate otherwise invisible galaxy formation in the early universe. The blobs reveal where primordial galaxies are assembling their first stellar populations under quasar illumination. Dark matter forms the universe's largest structures, but it doesn't emit any light of its own. Quasars provide the only way to map this invisible cosmic architecture across billion light-year distances. As quasar light travels through space, it encounters gas clouds distributed along dark matter filaments. These clouds absorb specific wavelengths of light, creating absorption line forests in quasar spectra. The pattern of absorption lines maps the three-dimensional distribution of matter between us and distant quasars. Dense regions create more absorption lines, while cosmic voids show fewer interruptions. This absorption line tomography creates the most detailed maps of cosmic structure available to astronomy. Quasars serve as background illumination sources that reveal the invisible dark matter scaffolding that organizes all cosmic architecture. The most distant observable quasars place fundamental limits on how quickly cosmic structures could form after the Big Bang. These ancient objects constrain theories about early universe physics. Some quasars appear when the universe was less than 1 billion years old. At such early times, the cosmos had experienced only a fraction of its current expansion. The existence of fully formed supermassive black holes so early in cosmic history creates timing challenges for theoretical models. These black holes needed time to grow from smaller seeds to billion solar mass monsters. Observations of primordial quasars force astronomers to develop new theories about rapid black hole growth in the early universe. The most distant quasars serve as fossil evidence of cosmic conditions during the universe's first billion years of existence. Heavy elements didn't exist when the universe began. All carbon, oxygen, iron, and other elements heavier than hydrogen and helium were created inside stars and dispersed through space. Quasar spectra from different cosmic epochs record the gradual buildup of these heavy elements. The most distant quasars show much lower metal abundances than nearby objects. This metallicity evolution traces how successive generations of stars enriched the universe with heavy elements necessary for planet formation. Early quasars sample cosmic conditions before significant chemical evolution occurred. The metallicity measurements reveal that substantial element production happened very quickly in cosmic history. Even the most distant quasars show some heavy element enrichment, indicating rapid early stellar evolution in the universe's first galactic systems. The number, density, and brightness distribution of quasars at different cosmic epochs constrain fundamental properties of the universe itself. These statistical studies probe dark energy and cosmic geometry. Quasar surveys count how many objects exist at each distance and brightness level. These number counts depend sensitively on the universe's expansion history and overall geometry. Changes in cosmic expansion rate affect how much cosmic volume exists at each redshift. Accelerating expansion due to dark energy alters the expected quasar distribution patterns. By comparing observed quasar statistics with theoretical predictions, astronomers can measure the strength of dark energy and determine whether space has flat, curved, or hyperbolic geometry across cosmic scales. The space between galaxies isn't empty. It contains a thin gas called the intergalactic medium that fills the cosmic web's filamentary structure. A quasar light passes through this intergalactic gas on its journey to Earth. The gas absorbs specific wavelengths of light, creating absorption line signatures that reveal its temperature and density. Different ionization states of various elements produce distinct absorption patterns. By analyzing these patterns, astronomers can determine the physical conditions in intergalactic space. These measurements reveal that the intergalactic medium maintains temperatures of tens of thousands of degrees and densities millions of times lower than laboratory vacuums. Quasars provide the only practical probes of these extremely diffuse cosmic gas reservoirs. The fundamental constants of physics are assumed to remain unchanged throughout cosmic history. But some theories predict that these constants might actually vary over billions of years. Quasar spectra provide laboratories for testing constant variation across cosmic time. The spacing between spectral lines depends on fundamental constants like the fine structure constant. By comparing absorption line patterns from distant quasars with laboratory measurements, astronomers can detect any changes in fundamental constants over cosmic history. Current measurements using quasar spectra show no evidence for significant variation in fundamental constants over the past 10 billion years. These studies place the tightest constraints available on theories that predict changing physics over cosmic time. Current technology has reached the limits of how far we can detect quasars with existing telescopes. The next generation of instruments will push these boundaries dramatically further. Future space telescopes will have the sensitivity to detect quasars from when the universe was only a few 100 million years old. These observations will probe the very first generation of supermassive black holes. Ground-based telescopes with adaptive optics will resolve the detailed structure of quasar-host galaxies at unprecedented distances. This will reveal how the first galaxies assembled around primordial black holes. The coming decade will witness the discovery of quasars that formed before reionization was complete, during the cosmic dark ages when neutral hydrogen filled space. These ancient beacons will illuminate the universe's transition from primordial darkness to the transparent cosmos we observe today.